Hello, as usual. What we're going to do today is find probability using the table, and we are focused for now on Z-scores. So we're going to look for the probability of a data value being below and above Z-score, or between two Z-scores. I'm not sure that we're actually going to cover that, but we'll do the things that are most pertinent for coverage in introductory statistics. So what we have is a situation, let's say, where we have a z-score for a given case in a normal distribution, and we know we can find its probability. Another situation we might be in is that we're given a sample mean, and we're given the assumption that it's randomly drawn from the distribution of sample mean, and therefore we can find its probability. But we can only do these things if we can figure out how to use the z-tables. So, of course, we had to start by getting a couple of z-scores, and we're going to do these for sample means. So we have to remember that that means, if they're sample means, that the denominator term is the standard error. When you have an individual z case, like a z-score for a particular case, z sub I, your denominator is the sample standard deviation. And of course, I have an error there, which I'll fix right now. My apologies. So that z sub I should be the individual score sub I minus the mean over the sample standard deviation. But when you have a sample mean opposed to an individual case, so you've drawn a sample of a given size from a population distribution, you have the z for that mean, which is that mean minus mu's population value divided by what's known as the standard error of the mean, and that's the population standard deviation divided by the square root of your sample size. So up above we have two sample means. Population they're drawn from is the same, mu equals 15, and standard deviation equals, for the population, no, sigma equals 2.5. The samples, however, have different sample sizes. They actually have the same. So first we have to find their z-scores, and their z-scores are going to be the difference between each individual mean, which is 16.5 for both cases, divided by the standard error. Standard error of mean noted sigma sub mean, x bar. And that is sigma, which is the same for both cases, 2.5, divided by the square root of the sample size. And that is what is different between the two cases. In one case, n equals 4, so the square root of n is going to be 2. In the other case, n equals 25, so the square root of n is 25. So let's see what we come up with. We note in the first case, everything is the same except the denominator of the standard error, which is 2, yielding the standard error of the mean to be 1.25. And in the second sample, the denominator of the standard error term is 5, yielding a standard error term of 0.5. So 1.25 in the first case for a standard error, 0.5 in the second case for a standard error. You see that the standard error term is considerably less as sample size goes up. And the z-score is quite different Z is 1.2 in the first case and 3 in the second case. The only thing that varied between these two examples was the sample size. So as you have larger samples, a Z-score beyond a sample mean is more unusual. It's more standard errors away from the mean, and that's because we expect, given the central limit theorem, that as sample size increases, any sample mean is expected to approximate the population mean more and more closely. So now we have these Z-scores, and we have to use tables to see what proportion of the population is expected to fall in any given range. And right here I have above or below the obtained Z. So we're going to go to table 1 in your textbook, which is, I believe, pages 757 to 759. Look for the first table in the textbook if those pages are slightly different in your edition. And we're going to look for the proportion of cases that are expected to fall in the range below the sample mean. It's the first thing we're going to look at. So here we have some of your Z tables. It's not complete because that's many pages long. And we see, for instance, very conveniently, that a Z of 0 has 50% above it or below it. It's at the 50th percentile, and that's by definition. And we could look through a Z of 1 has 84%, and that's because you have the lower 50% below the mean, which is at the 54th percentile, plus an additional 34.13%, which you can look at in your Z tables. And that is the amount that lies between 0 and Z equals 1. So there are many different ways of laying out Z tables. And if you look online, you'll see very many ways. Your textbook actually has a fairly simple presentation, which is that for any Z-score, say Z equals 0.05, you have 51.99% of values in the normal distribution will be below that value. And all the values given for Z's are positive. To find the negative Z proportion, it's symmetrical, and I'll show you how to do that, but it's simply traction. And so you only really have to look at these one way. You don't have to add anything. As I said, there are a variety. But for a Z-score of 0.68, 75.17, proportion of the population are expected to lie below that. So here we have this first random sample, Z equals 1.2. So we want to know what proportion of cases, sample means, actually are expected to fall in the range below this sample mean. So we look along this particular column. The columns are arranged kind of awkwardly in the table, and we look for 1.2. In the Z column, you can actually do this opposite, know a proportion and try to find the Z that corresponds. That is a little bit more unusual that you should do that, so we're not going to cover that here. But you find the 1.2, and I just kind of truncated some of the distributions so you can see the bigger numbers, and the 1.2 corresponds to 0.8849. So the answer to our question is that for this sample, the proportion lying below this sample mean 0.8849 or 88.49% of the distribution. So we're going to go on to our second sample. And again, we're going to look. This sample has a a Z-score of 3. So we're going to find the section of our table that includes Z equals 3. And we're going to look along it for the row where Z equals 3. and we find 99.8687% of the population, or 0.9986 or 7 with rounding. It would depend on what program or program table you're using to find out how many digits the table goes out to find out whether or not you're going to round. At that level, it's really not important for our purpose. So we're going to see that that's 0.9986. And there we have our percent of cases below each of our two sample values.